Lift a crate onto a shelf in 1 second, or take a full minute, the work done is identical. What separates the two is power, the rate at which work gets done. In this video, we define average and instantaneous power, measure them in watts, compute both for a falling ball and a push cup, and then prove the deepest version of the idea. Power is the rate of change of kinetic energy. Start with a constant applied force acting on a body. Over a time interval delta t, the point where the force acts moves a distance delta x along the direction of motion, so the force does work. Delta w equals F sub s times delta x, where F sub s is the component of the force along the motion. The average power of the force is defined as the rate at which this work is done. Average power equals delta w over delta t. Substitute the work and the ratio becomes F sub x times delta x over delta t. But delta x over delta t is just the average velocity. So average power equals the force component along the motion times the average velocity. Power is measured in watts. 1 watt is 1 joule per second. Power is a scalar, and it carries the sign of the work. A force component pointing along the motion delivers positive power. It feeds energy into the body. A force component opposing the motion, like kinetic friction, delivers negative power. It drains energy away. And the force perpendicular to the motion does no work at all. Zero power. One more distinction keeps the units honest. The watt measures a rate, not an amount. Your electricity bill charges for kilowatt hours, power multiplied by time. And that is energy. A machine rated at 1 kilowatt tells you how fast it can deliver energy, never how much it holds. Average power describes a whole interval. For the power at a single instant, shrink the interval. Instantaneous power is the limit of delta w over delta t as delta t goes to 0. Write the work as F sub x times delta x. The force is constant, so F sub x factors out of the limit. And what remains, the limit of delta x over delta t, is the instantaneous velocity. So instantaneous power equals F sub x times v sub x. The force component along the motion times the velocity right now. It has the same shape as the average power formula, with the average velocity replaced by the instantaneous one. And since velocity changes from moment to moment, the power delivered by even a perfectly constant force can change over time. The next example turns that observation into numbers. First worked example, gravitational power for a falling ball. A ball of mass 0.2 kilograms is released from rest 15 meters above the ground and falls to a height of 5 meters. Ignoring air resistance, find the average power delivered by gravity over the fall, the instantaneous power at the moment the ball passes 5 meters, and sketch the graph of power versus time. Everything here needs the fall time, so find that first. Start the clock at release. In free fall from rest, the height obeys y sub f equals y0 minus 1/2 gt squared. Solve for the time. T sub f equals the square root of 2 over g times the drop in height. The drop is 15 minus 5, 10 meters. 2 over 9.8 times 10 square root, 1.4 seconds. First approach, work divided by time. Gravity does work equal to negative mg times the change in height. The height change is 5 minus 15, negative 10 meters, so the work comes out positive. 0.2 times 9.8 times 10, 19.6 joules, or 20 joules to two significant figures. The sign makes sense. Gravity points down and the ball moves down. Average power is the work over the time. 20 joules over 1.4 seconds, 14 watts. Second approach, force times average velocity. The gravitational force is negative mg, negative 2 newtons. The average velocity is displacement over time, negative 10 meters over 1.4 seconds, negative 7 meters per second. Multiply the two. Negative times negative 14 watts again. Both roots agree, as they must. Now the instantaneous power at 5 meters. That takes the velocity there. Falling from rest, the velocity at time t is negative gt. So at 1.4 seconds, it is negative 14 meters per second. Instantaneous power is force times velocity, negative mg times negative gt sub f, which is mg squared t sub f, numerically 0.2 times 9.8 squared times 1.4, 27 watts, nearly double the 14-watt average, and worked symbolically. The factor is exactly 2. Rounding is the only reason these numbers miss it. Last, the graph. The force is constant while the speed grows in proportion to time. So power versus time is a straight line through the origin. P equals mg squared t. The faster the ball falls, the faster gravity pumps energy into it. And at any moment, the line sits at exactly twice the average power accumulated since release. That factor of 2 deserves a proof because it is not a coincidence of rounding. Take any body that starts from rest under a constant force. The falling ball is one case. Instantaneous power is force times velocity, mg times gt. So P of t equals mg squared t, growing linearly from 0. Average power over the same stretch is total work over total time. The distance fallen by time t is 1/2 gt squared, so the work is mg times 1/2 gt squared, divided by t, and the average is 1/2 mg squared t. Set them side by side, instantaneous power, mg squared t, average power, 1/2 mg squared t, exactly twice, at every moment of the fall, not just at the end. It is the geometry of a straight line through the origin. Its average height over any stretch is half its final height. Nothing about gravity was essential here. Put any constant force F in place of mg, and the algebra is identical. Second worked example, pushing a cup across a table. The cup has mass 0.2 kilograms. The push is 2 newtons, aimed 30 degrees above the horizontal, applied over 1/2 meter, and the coefficient of kinetic friction between cup and table is 0.1. The cup starts from rest. Find the average power of the pushing force and the average power of friction. We carry extra digits through the intermediate steps and round only at the end. Start with the work done by the push. Only the horizontal component moves the cup forward. 2 newtons times the cosine of 30 degrees is 1.732 newtons. Over 1/2 meter, the push does 0.866 joules of work. Next, friction. The normal force balances the cup's weight minus the upward part of the push. The weight is 0.2 times 9.8, 1.96 newtons. The upward component of the push is 2 newtons times the sine of 30 degrees, exactly 1 newton. That leaves a normal force of 0.96 newtons. Kinetic friction is the coefficient times the normal force, 0.096 newtons, pointing backward. Over 1/2 meter, friction does negative 0.048 joules of work. Power needs a time interval, and the time comes from the motion. The net work, 0.866 minus 0.048, which is 0.818 joules, equals the kinetic energy the cup gains, 1/2 mv squared. Solving for the final speed gives 2.86 meters per second. This is the same cup we pushed with the work energy theorem earlier. There we rounded the speed to 2.9, and the extra digits we are keeping here give 2.86. Under constant acceleration from rest, the average velocity is half the final speed, so the push lasts twice the distance divided by the final speed. 1 meter over 2.86, 0.3496 seconds. Now both powers. The pushing force, 0.866 joules over 0.3496 seconds. 2.48 watts, 2.5 to 2 significant figures. Friction, negative 0.048 joules over the same time, negative 0.14 watts, and here is a check worth noticing. Add them. 2.48 minus 0.14 is 2.34 watts, exactly the net work divided by the time, the average rate at which the cup's kinetic energy actually grew. Each force delivers its own power. The assigned sum is the rate the body's energy changes. Hold that thought. That closing check is a theorem. Take a body of mass m moving along the x direction. Its kinetic energy is 1/2 mv sub x squared. Differentiate with respect to time. The chain rule gives m times v sub x times dv sub x over dt. And dv sub x over dt is the acceleration. So the rate of change of kinetic energy is m times a sub x times v sub x. Now bring in Newton's second law. ma sub s is the net force component, f sub x, substitute, and dk over dt equals f sub x times v sub x, which is exactly the instantaneous power. Power is the time rate of change of kinetic energy. This is the work energy theorem in differential form. The integral version says the net work over an interval equals the change in kinetic energy across it. This version says it instant by instant. Whatever net power flows into the body right now is precisely how fast its kinetic energy is climbing right now. Power measures how fast work gets done. Across an interval, average power is work divided by time. Equivalently, the force component along the motion times the average velocity. At an instant, it is that force component times the velocity right now, and it is measured in watts, joules per second. Power is signed. A driving force feeds energy in, friction bleeds it out, and the signed sum of all the powers is the rate the body's kinetic energy changes, because power is the time derivative of kinetic energy. One limitation remains. Everything here lived along a single straight line. Lifting that restriction takes a new tool, the scalar product, and that is where this chapter goes next. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.